So the first concept that we want to talk about borrows from an understanding of the periodic table. Most of us have seen the periodic table since we were really small. We have this general notion in our head that the periodic table is rectangular. So it doesn't just continue on as this very long stream of elements, but rather elements that start for a while and then, well, they start back over in sort of a periodic kind of way. Quantum mechanics explains this periodic nature, but long before there was quantum mechanics, people were doing a perfectly fine job of creating the periodic table, people like Mendeleev, because they were able to look at the properties, the characteristics of the elements that form the periodic table and saw that they tended to group themselves in ways that had similar physical and chemical properties. So I want to spend a little bit of time taking a look at the periodic table, naming the different parts of it, and then talking a bit about what the trends are that are associated with it. So let's start off by appreciating the fact that the periodic table is in fact a rectangle, and as we look at the rows going across the periodic table, so here's row 1, 2, 3, 4, and so on, these are known as the periods. These will also become known as the principal quantum numbers, but we don't see that stuff right now. We just know that they're the periods. And in fact, the second period is the period where we spend most of our time. That's the period where organic chemistry is found. There are also groups, columns, within the periodic table. And you'll notice that there's a whole bunch of groups as we make our way all the way across, from group 1 all the way over to group 8, with some time out here in the middle for a substantial number of groups that, as we'll see, we don't spend a lot of time talking about, so much so that I'm actually standing in front of them and kind of ignoring them. So what are these groups? These groups turn out to be indicative of the number of valence electrons that exist within an element. A valence electron is an electron in the outer shell. It's not the inner shell electrons that are all filled up. It's the outer shell electrons, and these are the ones that drive most of the reactivity. So if I talk about a group 1 or a group 2 or a group 3 or 4 or 5 or 6 or 7, I'm talking about the number of valence electrons. Now, I need to talk about the distinction between these different sorts of groups so we can take parts of them and ignore them for a while. So I want to point out that these first two groups, coupled with these 6 groups over here, these 8 groups are known as the main group elements. The main group elements are the ones that we spend almost all our time on in general chemistry. Why? Well, for one thing, it's the really important stuff that's going on. This is the chemistry of the human body. This is the chemistry of the environment, for example. But it's also important because as I'm learning chemistry, the trends, the sorts of things that I can explain simply tend to fall out of main group chemistry. Now, in addition to the main group, we have this huge block of elements sitting here in the middle. This block right here is known as the transition metals. This block down here is known as the lanthanide metals. It's not that these aren't important. After all, this is where our metals are for the most part found, whether you're talking about nickel or gold or tungsten or whatever. But from a general chemistry perspective, these are difficult to appreciate because, well, frankly, they are so close together in terms of their electron density that being able to explain trends really easily is a difficult thing to do. So we tend to stand in front of a periodic table and ignore the transition metals and the lanthanide series to the best of our ability and focus on what's taking place in the main group. And that's where we'll spend most of our time in these descriptive chemistry lectures. So as we take a look at the main group, it's important to see that each of these groups has its own characteristics. And these characteristics, as I mentioned, are tagged to the number of valence electrons. Group 1 has 1 valence electron, group 2, 2 valence electrons, group 3, 4, 5, 6, 7, and 8, that's the number of valence electrons they have. And that number of valence electrons drives the trends, it drives the chemistry, it drives the properties. Well, we give names to some of the more famous of these groups. Group 1 here is the alkali metals. Group 2 is the alkali earths. Way over here on this far side of the periodic table, we have the noble gases, and here we have the halogens. And those are the ones you're expected to know. What are, in fact, some of the characteristics of these particular groups? Well, group 1 metals are known, in fact, as metals. These are alkali metals. They're alkali metals because it turns out that when you throw these metals into water, they end up making a base. One of the reasons they get grouped together so effortlessly is because these are the only metals where when you put them into water, they actually explode. And so that's the really driving characteristic feature of them. Evidently, they really don't want to remain in their elemental form, more so than anything else. And the reason, as we've learned in high school chemistry, is that when you have a single valence electron, if you can get rid of that valence electron and become noble gas-like to satisfy the octet rule, then what you have done is get to a much, much more stable form. And since losing that electron comes so easily to it, the alkali metals will explosively react with water, making a base in water and making a salt, sodium ion, potassium ion, lithium ion. The second column is the alkali earths. These alkali earths have two valence electrons. It's not quite as easy for them to become noble gas-like, but they do want to lose those two electrons and very much do so. And in fact, because they're called the alkali earths, it points to the fact that when they're put into water, they also end up making an alkali solution as they react to make the cation. Notice that these alkali earths include some of the important kinds of structural sorts of materials that you see. So like here's calcium, for example. Calcium which is found in bones, and calcium which is found in teeth, and calcium which is found in limestone. Over here on this side of the periodic table, these are the p block elements. By p block, we refer to the fact that when you're doing quantum mechanics, the last valence electron is found in a p orbital. Notice that this is the place where the chemistry of organic and biochemistry molecules is found. As we start over here on the far side of it, we find the noble gases. These are the electronic configurations that everything wants to be like. These are the things that drive the way chemistry is done. Everything wants to be noble gas-like. In the first period, everything wants to be like helium and have only 2 electrons. In the second period, everything wants to be like neon and have 10 electrons, and so on. Because these already are what everything wants to become, because they already have that closed shell, they aren't reactive. So as a result, we have gases like helium, neon, argon, and it's only under the most extreme conditions that you see them do anything other than be inert. And in fact, this is why these are also called the inert gases. Sitting next to those is a group of elements which are every bit as famous as the alkali metals. These are the halogens, things like fluorine and chlorine and bromine. These have 7 electrons, and they're just one short of being noble gas-like. So in the same way that these electrons, these alkali metals want to lose 1 electron and become noble gas, these want to gain 1 electron and become like a noble gas. When we look at them in terms of their physical and chemical properties, they are in fact reactive materials, and they're found as diatomic gases typically, F2, Cl2, Br2, and so on. The elements that we see over here in the middle of the P block, these central main group elements, actually don't have quite as specific a collection of requirements with respect to how they're going to turn out. They're not all going to gain or lose electrons. And in fact, it's the richness of their ability to gain and lose electrons, basically to change their oxidation states, that allows us to create the chemistry of the body, organic chemistry and biochemistry, and also the chemistry of the environment, understanding the different kinds of gases in the atmosphere, for example. So it's not quite as simple to look at something like a carbon or a nitrogen or a silicon and be able to say, yes, I know exactly how many electrons that will or will not gain. And in fact, what we will find out is that it's our ability to look at the oxidation numbers that tell us the particular state of the number of electrons and where they're located in species associated with those atoms.